Good morning students. I welcome you in the lecture series of electronic devices circuit. Let me choose first pen, ballpoint pen, and then we will start with our lecture of electronic devices circuit. In this lecture, we will see the DC biasing of BJT. Okay, DC biasing of BJT we will see. In the previous lecture, we have started. We have started with the DC biasing, that is fixed biasing. In the upcoming lecture, we will see the remaining types of DC biasing technique, different biasing techniques. Okay, so if you are not subscribed my channel, please go through the subscription. It is free of cost. Please on the subscribe button, and you can watch the entire video series of electronic devices circuit. Then you can watch the DFT videos. Then you can watch the micro video in the single YouTube channel. So let's begin. So we have started what I exactly mean by biasing. Biasing nothing is just we have to give the DC supply to the amplifier. DC supply to the amplifier is nothing but biasing. As we know that for amplification, input is my AC signals. AC signals are my input, and output is also my AC signal. But to operate this, to turn on this device, we required some kind of supply, that is nothing but the DC supply. So that's why the technique is called as biasing. So we have seen this particular things in previous lecture. We have also gone through the fixed biasing. Just I will revise the things. Fixed bias is nothing but the circuit diagram. If you will find circuit diagram like this one, the technique is called as fixed biasing. So what we are doing in this particular case, so the collector is connected with the one resistor via one resistor, and that is given the supply, that is VCC. This is my DC supply. This is my DC supply, and here I am applying my input signal anything over here, and I am taking output anything over here. So input applied. This capacitor is called as coupling capacitor, input capacitor, and this is my output capacitor over there. Okay. So its job to reduce the DC signals, to restrict the DC signals. So as far as DC analysis is concerned, what you have to do in this particular case is that first of all, as far as DC is concerned, capacitor will be open. Okay, capacitor will be open circuited. Capacitor will be act as an open circuited in the DC. So this capacitor will vanish, this capacitor will vanish. The remaining circuit is only this only, without capacitor only. Okay, this circuit is there. So what do you have to do? We have to apply a KVL at input side. This is my input side. I will draw portion first, and then we will start. Okay, so this is my input side where IB is the base current over there, and this is my output side over there. This is my input side. So the supply VCC come across from this resistor via RB and going to this one, and coming out via ground over there. Higher potential to lower potential current will flow. We know that. So we have to apply a KVL, and we have to find out the value of IB, and from IB I have to find out the value of IC. That IC is nothing but the beta times of IB. So we have to find out the value of IC from this one. So we will find out this value of IC. How? Just we apply the KVL across this. So KVL, this circuit diagram. So minus to plus, I have to write plus over there. Then plus to minus, I have to write minus IB. Then IB, this is my RB, and the current flowing through this is nothing but my IB. We have to calculate because it's KVL. So voltage drop we have to calculate. Okay. So this IR is nothing but my voltage drop across this resistor. Okay. VB, I will say that this VB is nothing but the I is IB and RB, product of that one, minus this potential drop across this one. This is nothing but what? This is the NPN transistor. Okay, NPN transistor. So this is my P and N. So this acts like a PN junction diode over there. So we will find over there, and silicon diode is there. Its voltage drop is always how much? 0.7 volt. Keep in mind, its voltage drop is always 0.7. That's why we have to put the value of VB is equal to how much? 0.7 volt. From this, if I want to calculate the value of IB, so IB will be, if I am shifting to this side, cross multiplication, then what will happen? VCC minus VB, and here you will find IB and RB going to be plus. So if I am calculating, then I will get IB is equal to VCC minus VB divided by RB over there. I am getting the value of IB. From this, if just I will multiply with beta factor over there to the IB, I will get the value of IC. From this, I will get a value of what? IC I will get. Okay. So next slide I will get. Okay. From this, I will get the value of IC, that is collector current. Collector current is nothing but what? beta times of IB. So if I am applying the KVL output side, then minus to plus again VCC minus here plus to minus, that is minus I have to write IC RC minus VCE is equal to 0. From this, if I am calculating the value of VC is equal to what? VCC minus ICRC. VCC minus ICRC, I will say that VCC minus ICRC. So this is the thing. So we have to solve the problem based on this. So I will directly start with the problems. Okay. So this is the circuit diagram. From this you have to calculate the different parameters. This is the exam question. Okay. Directly you will find a exam question like this one. So what you have to find out? We have to find out the value of IB. We have to find out value of IC. We have to find out VC, then VB, VC, and VBC. So these whatever the capital letters. Suppose I am writing VCE. Okay, VCE. So this is the double subscript notation. So if I am subtracting this thing, if I am saying, so this is nothing but the drop across this VC and VE. That is nothing but the VC minus VE. I will write. Okay, if is written as like this one, VBE. Okay, so capital is equal to that is nothing but VB minus VE. Okay, so this is the nothing but my double subscript notations, VB and VC. From this we have to calculate the value of VC and VB and VCB. Okay, so we will calculate this thing by using this circuit diagram. We have to use this circuit diagram. So if I am DC analysis, so capacitor will open circuit, that means just cut off this capacitor from this circuit, So just a minute, I will rub this portion for you guys. Yeah, so just this, if I am redrawing the circuit once again. Okay, 1 second. So what will happen? This circuit will be like this one. For input side I am drawing. Okay, this is my VCC, this is nothing but my RB, and current flowing through this is nothing but my IB. Okay, and drop across this is nothing but my VBE. Okay, VBE. So if I am applying KVL across this, then what will happen? VCC minus IB RB minus VBE is equal to 0. So from this, if I am calculating the value of IB, I will get this equation. So if I am putting the value of this VCC, VB and RB in this one, so VCC is my 12 volt, RB is my 240K. If I am putting this value, so I will use the calculator, and I am getting the value as 47.08 microampere. And IC is equal to, we know that is nothing but the beta times of IB. And if you are observing the circuit, the beta value is already given to you. It's 100, 200, 150 like this one, or 99. So use that value, and if you are putting that value in this equation, so what we are getting? Just a minute. If I am multiplying this with the beta factor, that is nothing but my 50. So I will get 50 into 47.08 microampere. That is nothing but the 2.35 milliampere is the correct answer for ICQ. Is the correct answer for my ICQ. So how much part we have calculated? We have calculated the IB, we have calculated IC, we have calculated. Now it's turn to calculate the VC. And how to calculate? By applying output KVL. So this is my circuit diagram. I will rewrite the diagram once again at the output side. Okay, this is my output side. So this is nothing but my VCC, this is nothing but my RC, that is collector, that is nothing but VCE. Okay, drop across collector and emitter terminal, this is nothing but my VCE. Okay, and what I have to do? You have to apply KVL across this. Current flowing through this is nothing but my this resistor is nothing but my IC. So if I am applying KVL, so what will happen with this? VCC minus ICRC minus VCE. From this if I am calculating the value of VCE from this one, so I will get the VCC minus ICRC from this one. So VCC is nothing but how much? 12 volt minus IC we have calculated that previously, that is nothing but how much? 2.35 milliampere, and RC is nothing but 2.2 K. So if I am putting this value 12 volt minus 2.35 milliampere into 2.2 K, so I will get the VCE value is nothing but 6.83 volt. 6.83 volt. So if I want to calculate the value of VB from this one, so VB, how to calculate the VB? So normally we know that VBE is equal to what? We have discussed this thing, that is nothing but, if I am writing the double substitute, that is nothing but the VB minus VE, and my emitter terminal is connected to ground, so potential across this is 0, VE is 0 from this one. So VB is equal to what? VB, and VB's value is always 0.7. Keep in mind, this value across this VBE is always 0.7 because it is made up of silicon diode. Okay, if by default it's silicon diode, if they are mentioning that the diode is of germanium, so you have to put the value of VB is how much? 0.3 volt. Point how much? 3 volt in this one. Okay, so 0.7 volt if you are putting, so VB is how much? 0.7 volt there. Then VCE, so VCE is equal to what? VCE is equal to, now it's your turn, VC minus VE. So VC is equal to, directly this value 0, so VC is equal to VCE. So from this I will get the value of VC is equal to 6.83, that is we have calculated over there. Okay, and VBC, so how to write down? VB minus VC. So VB is value is how much? VB's value is how much? 0.7 minus VC is nothing but 6.83, so minus how much? 6.813 is the correct answer for this one. So we have calculated the entire problem based on this. You will find definitely problem based on this, so you have to solve the problem by changing the different value of this resistors and the supply voltage, not more than that they will give you value. Okay, so I think we have to stop over there for the today's lecture. Thank you very much.